Hello, my name is Sham Iyer. I am the chair for SNIA's SDXI Technical Working Group, also a member of SNIA's Technical Council, and also a distinguished engineer at Dell. I'm here to talk about standardizing memory-to-memory data movement with SDXI version 1.0. If you're here for this talk, I'm assuming you have looked through this abstract. In terms of the agenda that I'm going to cover today, I'm going to talk about the introduction to SNIA's SDXI version 1.0. I'm also going to talk about the use cases, particularly the application patterns and the benefits of data movement and acceleration. And then I'm going to end it up with SDXI, the path ahead, and talk a little bit about what we would do in version 1.1 and the ecosystem that we're trying to develop. So if you look at what's a current data movement standard today, and that's been the case for a long time, the software-based memcopy is our current data movement standard, and for a good reason that it's had stable instruction set architecture. And the challenge there is that it takes away from the application performance. It consumes the CPU cycles while it's doing the data movement. Also incurs overhead in trying to provide context isolations. We've always had offload DMA engines, but they've been vendor specific. So they're not ideally standardized for user-level software. So what we've done is we went ahead and thought of a new interface to enable a new class of devices. And that interface is the Smart Data Accelerator interface. It's a SNIA standard for a memory-to-memory data movement and acceleration interface that is one, extensible, forward compatible, and independent of I/O interconnect technology. To start this work, SNIA SDXI Technical Working Group was formed in June of 2020 and tasked to work on this standard. And we had 23 member companies participate in it, and 89 individual members that joined the group. And version 1.0 was released in November of 2022. So if you click that link after you get your presentation, you'll find that there is a specification, the 1.0 specification, as well as some helpful C header files on how to implement software to interface with the function implementations of SDXI. So we're pretty proud of this effort. It was, it comprised of experts from different companies. And we were able to manage that version 1.0 spec in record time. In terms of what that specification is designed for, so any kind of memory-to-memory data movement interface needs to work with applications. So we have designed it such that applications can make use of this interface without having to deal with a lot of software context isolation layers. It's also allows the application to directly access the interface so that you don't have to go traverse through multiple software layers. In terms of the architecture, it will enjoy the same kind of architecture stability that you will get with ISA-based instructions, and also deals with how to manage the security of context isolation. To begin with, a lot of these memory-to-memory data movement is likely to be DRAM based, but the specification is designed such that you can also target memory access on storage class memory and memory behind I/O devices, or even if they are memory across a link or a memory link or a fabric like CXL. The specification itself is independent of where it's implemented and how it's implemented, and it's also CPU agnostic, so different microarchitectures ISA CPUs could implement the same interface. We have also designed it such a way that it's form factor independent, such that whether it's CPU integrated or as a discrete implementations as GPUs, FPGAs, or smart I/O devices, you could implement SDXI over there. The advantage is that when you build a standard like this, you can now innovate around the spec and add incremental data acceleration features. Like I said before, the data movement is also expected to be between different address spaces. You can envision them as two different applications, two different VMs, two different, potentially different hosts in the future, and so on. The data movement is also designed for to be done without mediation by privileged software, of course, once the connection has been established. And we have designed it in such a way that it allows for abstraction and virtualization by privileged software. It will have the capability to quiesce, suspend, and resume the architectural state. So this is particularly useful if you're trying to move the application or the VM and do live migration of the workload. Forwards and backward compatibility has been envisioned. The interface is very extensible, such that you can now have additional offloads, not just to memory data movement, but do additional kind of data transformation as you're doing those kind of data movements and copies. And it's a very concurrent DMA model. That means you can have multiple parallel DMA accesses going on at the same time. This is a quick picture of how the specification defines these interfaces and the structures. If you look at this picture from left to right, on the left side, I have an implementation of an SDXI function. And this function will have an MMIO space where it will implement a few basic minimum registers. Some of these registers I'll describe are the ones that point to a context table. And these context table point to additional tables in memory which control the state. And these contexts are nothing but some of the data structures that are required for any kind of producer to be able to submit work for this interface. As you can imagine, the work is produced or enqueued using the help of a descriptor ring, and the pointers of maintaining the state are basically the right index pointer and the read index pointer. Software updates the right index pointer when it has new work. The read index pointer is updated whenever the descriptor has been fetched by the function from memory. As you can imagine, at least for a data movement or a data copy, at least minimum 2 buffers are required. So there's an example of that. Once the operation is finished, then you will have a completion status. And this is a pointer in the descriptor itself. And the function basically updates the completion in the memory pointed by the completion status pointer block. For letting the function know that there is new work, there is a provision for a doorbell that is rung by producers into the SDXI function. So the space that I'm showing in highlight is the region that can be mapped directly into the user space. So you don't need privileged software managing this. So all of the work can be done by user space without involving the privileged software. The part that it's a layered architecture, so the part that does need privileged software is to ensure that the context tables are set up properly. We have a concept for something called an A key table that basically tells you which address spaces the producer is allowed to access. And then there is a concept of an R key table, which basically controls which remote functions can reach into the local resources that this function manages, whether it's memory or other things. And then on a per function basis, there is one error log where all of the errors related to the context will get logged. As you can see, the R key, the A key, and the error logs are all in privileged software control. So you could mediate whenever required. So all of this is one descriptor format with a feature for expansion, easy to virtualize, and it's a layered model. In the spec, we define an example for PCIe-based implementations. But like I explained, the specification itself is interconnect independent. So future interconnects or fabrics can still implement SDXI depending on what their design choices are. So this is an example. It's actually an example where we are showcasing how SDXI works with multiple address spaces. In this example, the producer is in address space B, which is in the middle, and it's trying to move data from an address space A, which is on the left here, to the address space C, which is on the right here. This can also be visualized as maybe the hypervisor trying to move from one VM to the other VM, or maybe a VM trying to move it between two different VMs, or any combination of address spaces that you want to logically separate. So the producer enqueues work into the descriptor ring and rings the doorbell. This function B, which is local to the address space B, fetches the descriptors by doing a DMA read. Once it reads the descriptor, inside the descriptor, it specifies which address spaces it's trying to do the data movement. That's specified by the A keys. The A keys need to get validated by the function to ensure that this function is allowed to access those address spaces, and this is specified by the A key table. Once that validation is successful, the A key entries have encode to the R key indexes that this target function will use to go fetch the entry from the address space A's R key table. And in that R key entry, the A key that is allowed to reach into this address space is validated. And so that means the access is allowed. Once that access is allowed, then this memory access can happen. The same thing happens on address space C as well, where this requesting function is checked against the R key entry to make sure this function is allowed to access. Once that access check passes as well, then a DMA read is instituted to the address space A, and then the data that is returned from this address space A is written into the address space C. So this is an example of how a multi-address space data movement occurs in the SDXI architecture. So like I explained to you, there are 23 member companies and 89 members, but also there have been a lot of them are contributors. So I want to thank all of the member companies here shown in the logo for their contributions towards version 1.0 specification. And to just give you an idea, we are still growing as we go into the new versions of the specification. So here is an example of the use cases that you can look at to see how SDXI benefits you. So for example, if you have an application and it wants to move data between a source memory buffer here and a destination memory buffer here, typically you would use memcopy, which, as I explained before, takes away from the application performance. Now, with the help of SDXI, which is what I'm showing as an accelerator, now you can perform DMA copies by first enqueuing the work into a descriptor ring, ringing a doorbell, and then making the descriptor fetch happen by the accelerator, and then the accelerator does the DMA copy. And once it's done, it sends the completion signal back to the application saying, I'm done. So this is an example of a pattern that SDXI will enable you. Another pattern here is an application wants to perform, store or retrieve data from persistent storage. Then typically today it has to perform mem copies from its user buffer to the kernel buffer, and in some cases, the kernel driver ends up doing one more copy from a kernel buffer to a DMA-able memory buffer that it manages. And then it rings the doorbell, asks the storage to pick up the data, and now the data is persistent. And when you have to read the data back, now you have to do the reverse, which is, you have to enqueue a command, ring the doorbell, get the data DMA'd into a DMA-able buffer. Then the data is copied into a kernel memory buffer, and then finally copied into a user buffer. So there's a lot of isolation software layers and memory buffer copies that can be avoided. Persistent memory did some optimizations here by allowing source data to get copied into a persistent memory buffer using mem copies whenever you wanted to store it in persistence. And when you wanted to retrieve the data back, you could do the same mem copy back from persistent buffer into a volatile memory buffer. We can take this further by optimizing this with the help of SDXI. Now we will, instead of using mem copies, we can use the same principle to move data with the help of the accelerator from volatile memory buffers to persistent memory buffers. And all these while reducing buffer copies, but also offloading the memory copies into hardware. This third pattern is related to virtualization. And this is one example where virtualized, there are two VMs, and these VMs want to move data between each other. Today, we have to do copy from the VMs, user buffer to maybe the host or the hypervisor's kernel buffer. And then maybe, at least even if you optimize it, there is one more DMA read going into an IO device. It may go in through a network, come back to another IO device or the same IO device. And then a DMA write will need to happen. And then the kernel has to now write the data into the second virtual machine's buffer. So as you can see, even in the case of virtualization, there are multiple buffer copies. SDXI does allow for a lot of optimization here. So you can now ask the accelerator or the SDXI device function to pick up the data from the buffer in VM's user memory, turn around and write the data back into another VM's memory buffer without having to go through a lot of the host and hypervisor kernels during runtime. So this is a nice little optimization for performance that SDXI enables as a use case. There's a lot of increasing use cases because now we are dealing with data in use memory expansion. It's like we explained, DRAM is no longer just the only memory of choice. You have persistent memory, you have memory across memory fabrics like CXL. You can also have large amounts of memory behind an IO device. And so this allows for tiering of memory. And with the help of an accelerator, you can do this kind of tiering much more efficiently while tending to the needs for the application to use less and less of CPU cycles. This is another emerging use case that SDXI is enabling. So as CXL becomes more prevalent in the data center architecture, you have an instance where CXL is allowing for memory expansion. So here I'm showing you two pictures or two kinds of implementations where SDXI could play a role. The picture on the left is where in the SDXI is sort of a PCIe device. And you can have SDXI move data from one CPU attached memory to another CPU attached memory, or two different regions of the CPU attached memory, like we discussed before. You can also have SDXI move data from a CPU attached memory to a remote memory that is made available to the host CPU through a SDXL memory expander. This memory could be shared or pooled. So that kind of goes into the aspect of now SDXI could be not just for a single host, but for multi-host as well. The picture on the right here is where an SDXI is actually a CXL device implementation. Because remember, like we said, SDXI is interconnect independent. So an implementation could exist as a PCIe device, as a CXL device, or any other kind of proprietary device. The interface and the data structures is where we standardize them. So in this model, you could have SDXI CXL device being used for data movement between CPU attached memory. And in the case of CXL, you could also have device attached memory, and the CXL device that implements SDXI also has memory in it. So lots of exciting use cases that you can enable with this particular emerging use case. So what's the path ahead? So SDXI, we are looking at version 1.1 and also looking at how to enable the software ecosystem. So as part of our 1.1 investigations, right now the twig is looking at some of these features. I should caveat that these are all subject to change. And if you look at them closely, it's almost in line with how we started with 1.0 and how we already envisioned some of these features. So for example, we're looking at the management architecture for the data movers, which means how would we connect two different address spaces to be able to do the data movement. Today, we have defined the spec in such a way that once a connection has been established, this is how you would do the data movement and all the interfaces and the structures that are required for that. This goes into the next level, which is what kind of a connection manager operative that you would need to establish that kind of connection. You could still do it without the connection manager, but that means there is a whole bunch of standardization left out of the table. The second part is about how do we enable new data mover operations for doing these kind of acceleration. So that example could be data integrity feeds or diff and dix, some kind of compression or encryption, other kinds of operations that you might want to do while you're moving the data from a source location to a destination location. As I explained before, SDXI can also now enable host-to-host data movement, particularly in interconnects like CXL, where it makes it easy for SDXI to become an interhost data mover. The fourth bullet is about how we are going further than what we defined in 1.0 in terms of what kind of improvements we can do. We're doing investigations around direct work submission, SIOV, or other kinds of models, which will further improve our performance whenever these implementations show up. We are considering what kind of cache currency models we need to have for these data movers. We're trying to look at security features or features that improve security and how SDXI interplays with them, like IDE or confidential computing. And we're doing some amount of threat modeling to ensure what kind of threat SDXI mitigates. And then we're looking at specifically data mover operations involving persistent memory targets, other considerations like QoS or heterogeneous environments are all on the table. Some of the additional ecosystem activities that the twig is looking at is we're looking at a project called libSDXI. This is where we are looking at developing an OS agnostic user space library within SNIA, and stay tuned for it on how this work starts shaping. This is currently happening within the twig, but at some point of time, the expectation is we will realize it just like the specification. We are also supporting Linux upstream driver efforts. So with this work is not happening inside SNIA because the specific licensing requirements, but a lot of the members who are supporting this effort are SNIA members, so they are doing this outside of this community. We are also looking at how we could investigate an SDXI emulation implementation. So this is purely from the point of view of enabling ecosystems, whether it's hardware or software development, as we go about implementing newer versions of the specification. We are also allowing investigations for how do we build compliance between software and hardware implementations for interoperability reasons. And finally, there is a subgroup inside SNIA that is looking at how do you envision SDXI in a computational storage architecture, one, and two, what kind of features would SDXI need to implement to support computational storage use cases? So this subgroup is kind of just getting started, and we have already gotten some amount of architecture and collateral work developed that we would love to bring back to the community here. So with that in mind, here's my call to action. Join the twig to influence the next version of the specification. As I said, version 1.0 is already available for implementation. If you don't want to join the twig, you can certainly provide us feedback through the SNIA feedback portal here, and participate in the SDXI ecosystem. With that, I would love if you could rate this session here. Your feedback is important to us, and I would love to chat separately and offline and field any questions through the Q&A channel. Thank you.